Good morning. So in last week's lectures, which is already posted in the Blackboard, we talk about single phase transformers, right? So the equivalent circuit of an ideal single phase transformers is basically two sides. So that's a coil, and this is another coil, and here we are drawing two sides. Now this side is called the primary side of a transformer, and this side is a secondary side of the transformer, right? Now, it's just a number of turns for every coil, so there are a number of turns here. I'm going to call them NB, and B here is standing for primary. And in this side, we said this is the secondary side, so we're going to call the number of turns here NS, right? So NB is primary number of turns, NS is secondary number of turns, right? Okay. And as we learned from last week's lecture, there is no physical connection between a primary side and secondary side. The power is transferred through induction. Here, this is the primary side. In the primary side, we connect the source of the power. That could be a transmission line system, that could be a distribution substation, and so on. Or a source, normal source, right? So here we're connecting the source. So this is the incoming side of the transformer, and this is the outgoing side of the transformer, right? So outgoing here will be connected to the load or another side of a transmission systems. Okay? So simply here, let's put a source, so we can connect a source here, right? An AC source, and here we will connect a load. That's a load, right? And this load could be a resistive load, could be RL load, like motors, for example, inductive resistive loads, equivalent circuit of motors, and so on, right? So here we're going to be focusing on the transformer side here. So the voltage in the primary is EB, and the voltage in the secondary is ES, right? So once you connect them, there will be a current here that flows in the primary, that's I primary, and here a current that is delivered to the load, and this is I secondary, right? So note that in the primary side, we use P standing for primary. This is the voltage in the primary side. This is the current passing through the coil in the primary side, and that's the number of turns in of the primary side. In this side, that's the number of turns in the secondary side. That's the voltage output of the secondary side, and that's the current flowing in the secondary side of a transformer. This is an equivalent circuit of ideal single phase transformer. We ignore the losses, right? We are assuming that the losses here is very low, because typically efficiency for transformers could reach up to 95–96%. So if it's acceptable to neglect the losses here, especially in low level transformers, right? So that's the ideal circuit of transformer. Okay, what's the relation between voltages and current? Remember, the transformers does not generate power. No, the transformers, from its name, just transforms power from one side to another side. So whatever the power is coming here will be transformed to that side, of course with some losses, right? But we're assuming that that's an ideal case, that's an ideal transformers, so we ignore the losses. So in general, typically we're saying whatever incoming power here will be transformed to the secondary side. Based on this, the power that is coming from here, we're gonna call it S, right? So this is S primary. That's the apparent power in volt ampere that is supplied from the source to the primary side and will be transformed to will be transferred to the load in the secondary side. So this is S secondary, right? Okay. Now what we are saying is that ignoring the losses in the ideal transformer, SB is equal to SS. So the volt ampere that is transferred by a transformer is same. Keep this in mind because we're going to use it for one equations later. Now, what is the relation between voltages, currents, and number of turns? Basically, that's the golden equation for transformer that everybody should know it. For an ideal transformer, the E secondary over E primary is equal to the percentage of N secondary over N primary, right? Cross multiplication will give you what? ES NB is EB NS. That's the cross multiplication. So ES over EB is equal to NS over NB. Be careful. We are not saying this doesn't mean ES is equal to NS. No. Or EB is equal to NB. No. That's basic math. The ratio is the same, right? Now current is opposite. Since we said in the beginning that it's the same power that's going to be transformed, now if you change the voltage, the current also should change, right? If you step the voltage up, if you raise the voltage up, what should happen to the current in order to keep the same power? It should go down. It should be stepped down, right? So that's why you will notice that the relation is opposite. Here ES over EB is equal to NS over NB is equal to IB over IS. See? The ratio of the current is opposite to the voltage, right? Now if you do cross multiplication here between this one, this ratio and this ratio, we're saying that EB times IB is equal to ES times IS. What is this? That's the apparent power, right? Magnitude of the apparent power, if you remember from three-phase circuit lecture. S in the primary and this is S in the secondary. And we are saying that they are equal because we ignore the losses. That's the golden equation of an ideal transformer that everybody should know it. Okay? Good. Now, this is single phase transformers. One coil. That coil is supplied by one source, and the coil here is transforming power or delivering power to one load. Right. Now, let me bring another two transformers to the system, right? And we'll do something here. Yeah. So, this is one single phase transformers, and I'm gonna bring another single phase transformers identical with this, the same number of turns ratio. Okay, right? See, does this remind you of something from lecture of week 9, right? Now what we're doing here, we are connecting a 3 single phase transformers in Y shape, in a star shape. You see? This is number 1, this is single phase transformer, another single phase transformer, a third single phase transformer. We do this in the primary side, let's do it also in the secondary side. So I need some space here. Let me just make it full because we need some space here, right? So this was the secondary 2, right? So we're gonna bring another 2 as well, right? So this is here, and this is here. Okay. Now, what is this in front of us? That's a Y to Y connection because this is the shape of Y from three-phase circuit lecture. This is another shape of Y. This is now a primary side, this is a secondary side, which means the number of turns here is NP in the primary. The same thing here. NP, NB. In the primary side, they have same number of turns. In the secondary side, this is NS. Number of turns is NS, right? Here, we have a 3-phase incoming transmission system, for example, transmission line, or a 3-phase source connected to the primary, to the input side. That's the input side of the transformer. And here, this is 3-phase secondary side is delivering the power to 3-phase load, which could be 3-phase motors, for example, or outgoing 3-phase transmission system, right? So basically here it's the same idea, but now instead of having single-phase transformers, we have 3 single-phase transformers that we connect them in a shape of Y. If you focus on this is Y to Y connections, right? So the first connection of a 3-phase single-phase transformers is Y to Y connection. or we call it star to star connections. So the primary side and both the secondary side are connected in Y shape. Good, right, okay. So let's put the equation. That's it. What are the relation between primary and secondary? So remember from three-phase circuit lecture. Now I'm gonna call this one A, B, C, for example, right? Or let me make it A, B, C. So let's say this is A, this one is B, and this one is C. And on that side, let's make it small, capital and small. So this is gonna be A, and this one here is B, and this is C, right? This will be connected to a three-phase load, and this is supplied by a three-phase source, like three-phase substation. Okay, or a three-phase transmission system. Primary side, secondary side. What's the relation between a primary side and secondary side? Easy, right? So let's just put the equation based on our golden equation for single-phase transformers. In the three single-phase transformers, we're going to be focusing mainly on the line-to-line voltage in the primary side and the line-to-line voltage in the secondary side. What's the relation between them? So from A to B, that's line to line in the primary. C to A, another line to line in the primary. B to C, that's line to line in the primary. These three line voltages from three-phase circuits lecture are equal in RMS values, but they have shift of 120 minus 120 magnitude based on the sequence. The same thing here. The voltage between A and B, that's line to line in the secondary side. B to C, line to line in the secondary side. C to A again is line to line in the secondary side. And these three line to line secondaries are the same in RMS values, but they have a phase shift of plus minus 120. Here we're going to be focusing only on the RMS values, right? RMS values. So what's the equation here basically? Equation of Y to Y connection is from the single phase golden equation that we've just shown before. E line to line, S which means secondary, over E line to line, P primary. E line to line in this side, for example here, from here to here, this is E line to line. It's E A to B, right? This one is E B to C, right? And from here to here, this is E C to A, right? All line to line voltages in the secondary side. It's in the secondary side. They have the same RMS values, the same values, but phase shift of 120 minus plus 120, right? So forget about the phase shift. Now we're going to be focusing here mainly on the RMS values. The same thing here. This is the voltage here, A to C. So this is CA. This one is E, BC, for example, right? And from here to here, this is AB. These are all line to line in the primary side. In the primary side. Now, what in the primary side? They have the same, again, RMS value, phase shift of plus minus 120. Now, let's focus on the RMS values and the amplitude, the magnitude here. What is the relation between this voltage in the primary side and this voltage in the secondary side? In Y to Y connection, easy. The simple relation between them is coming from the Thevenin's ratio. Right? So let's go bring our equations from single phase transformers. E line to line secondary over E line to line primary is equal to number of turns in secondary over number of turns in primary. Okay? So from here, what we can conclude here, from here, what will be E line to line secondary? E line to line secondary is what? Is NS over NB times E line to line primary. That's the equations. See? And because it's Y to Y connection, there will be no phase shift between this voltage and that voltage. There is no phase difference between them, right? Because it's Y to Y connection, okay? But let's focus here on the RMS values. Of course, there will be some phase shifted between this voltage, and this voltage in one side, right? Which is plus minus 120. There will be some voltage phase shift between this voltage, and this voltage, because again, it's a plus minus 120. But if you would take this voltage, for example, ECA here and ECA here, they will have no phase shift difference because it's Y to Y connection. But the amplitude will be different. The RMS value from primary side and secondary side will be different based on the turns ratio. How many turns how many turns we have in the primary side and how many turns we have in the secondary side, right? So that's your golden equation for Y to Y connection. Okay? Okay. Now based on this, what about the currents? The currents will be just opposite. So the I line secondary, the I line there secondary is NB over NS I line primary. Okay. This is true only in Y connection. Now this configuration is rarely used actually due to the problems of unbalanced voltage, potential unbalanced voltage and third harmonics and these things. So, but it is used, it's still there, right? So that's the first type of three-phase connection of transformers, star to star or Y to Y. The primary side is Y, the secondary side is Y. Okay, come back. Now, so in last part we talk about Y to Y connection. Second type of connection is delta to delta connection for transformers. So this is delta connection, right? So delta. Again, if we recall the three-phase circuit lectures, so that's a delta connection. Three coils here, and we have another delta connection here, again 3 coils, right? Okay, so this is 1, 2, 3, right? Okay, and here we have this one line, the other one, the third one, okay? Delta connection. Let me just raise this to have some space, but this is delta connection here. So number 2 is delta. So the primary side is delta and the secondary side again is delta. This is the number of turns, so it will be N primary, N primary, N primary. Same number of turns for the primary. The same thing here, N secondary, N secondary, N secondary. So the ratio between them is N primary, N secondary. Okay, that's the primary side, that's the incoming side, that's the input side of transformer, and this is the output side, outgoing side, which is secondary side of a transformer. Let me call this one again A, B, or C, sorry, just a matter of convention here. C, B, that's B, and here this will be small a, that's gonna be small b, and this is small c. Again, so similar to Y to Y connection. Remember in delta connection, there is no neutral, right? And basically the voltage is the same for every delta connections. This voltage is nothing but this voltage, right? And this voltage is nothing but this voltage, right? And the voltage here is nothing but from A to B, okay? So in delta connection, line to line voltage for one delta side is equal to the load voltage, okay? But here it's a transformer. So what's the relation between this voltage in the primary side and the voltage in the secondary side? The relation simply will be through transformer ratio, number of turns here, right? And again from our golden equations, this is line to line in a primary, another line to line in a primary, line to line in a primary. They are the same in RMS, phase shift different, plus minus 120. But let's focus on the point that they are the same in the RMS. This side is RMS the same. In that side, this is line to line secondary, this is line to line secondary, line to line secondary voltage. Again, they have the same value of RMS, phase shift plus minus 120 as we did in the three-phase circuit, right? But we focus on RMS here. What is the relation between this side voltage, the line to line secondary side voltage, and the line to line primary side voltage? The relation is basically through number of turns. That's delta to delta connection. So again, from our golden equation for an ideal transformers, E line to line secondary over E line to line in a primary is equal to number of turns in a prime and secondary over number of turns in primary, right? And remember, the voltage will be opposite. The current, sorry, will be opposite, right? Okay. So, what does that mean? What is our equation here? How do we calculate the RMS value of E line to line secondary, line to line in the secondary, which is this voltage, and this voltage. Here I am focusing only in the RMS value, not the phase shift. Okay? Line to line here is equal to number of turns for secondary over number of turns for primary times the line to line primary. This is your equation for delta transformer, right? Remember here we're talking about RMS values. Okay, what about the currents? Now, once we know the voltage, we can bring the current, because what we said in the beginning, that we are transferring the same amount of power, ignoring the losses. So that if you step up the voltage, if you increase the voltage, you need to decrease the current in order to have the same power transfer, right? So that's for the voltage. What about for the currents? For the currents, then I line in the secondary side is equal to N B opposite to this over NS I line in the primary side. That's the equation if we want the current, right? Okay? Okay. So delta is very commonly used, and we will do one example here, basic calculation. In the next video recording, I'll do one example on delta transformers. Okay? Okay guys, welcome to part 3 of the lecture about connections of transformers. So in part 1 we talk about Y connections, in part 2 we talk about delta connections. Now the third connections is mix up between Y and delta. So number 3 is Y delta, or Y is star and delta, right? So that's number 3. So the primary side will be connected as Y, star connection, and the secondary side connected as delta. So let's do the connections here. So the primary, remember everything is 3-phase here, right? Or 3 single-phase transformers connected to form a 3-phase transformer. So here we have the primary side connected in delta. So that's the primary side. This is coil 1, 2, 3. This is Y, right? Okay. So let's say this is here phase A, capital A, and this is capital B, capital C. This is now the primary side. The secondary side is delta. Okay, so that's the secondary side. So in the secondary side, again, this is a small a, a small b and a small c. Okay? This phase is equivalent to b here, which means the same phase here, that's b. Okay? So this is the primary side, this is the secondary side. So in the primary side, we have number of turns in the primary in P, in B. So the primary side is in B, and the secondary side will be in S. So the number of turns ratio here is NS, the same number of turns, the same number of turns. Right? Okay. So as we said before, in the primary side, here we have the supply side, which could be a transmission system, which could be a distribution substations. So basically this is the source side, the supply of the power, and here in that side will supply power to the load, three-phase load. Primary is star, secondary is delta. Typically what we're looking for is the relation between line-to-line voltage of the primary, which is the input side or incoming side, and line-to-line voltage in the secondary. Okay? What will be the relation between them? And again, we're going to be focusing on the RMS values of the voltages. So, the voltage from here to here again is line-to-line voltage. This voltage is ECA. The voltage here is EBC. And the voltage from A to B is AB. From this line to this line, that's EB. All of these three are line voltages in the primary side. They have the same RMS values, exactly the same RMS values because it's a balanced system, but there is a phase shift of plus minus 120. Let's go to the secondary side. And the secondary side again, this is the voltage between E, small a, small b. This is ECB, or BC, sorry, BC. And so this is BC, EBC, small b, small c, and here we have CA from here to here. Again, the line-to-line voltage in the secondary is AEB, ABC, ACA have the same RMS values. Phase difference plus minus 120 based on the sequence. If we're talking about ABC sequence or positive sequence, it will be plus 120 for the C and minus 120 for the B, as we did in the lecture of three-phase circuit. Now, through the transformer, what we are interested mainly on to know is the relation between the line-to-line voltage of the primary and the line-to-line voltage of the secondary. What is the relation between them? So let me write it here. Now, again, we go back to our golden equation of ideal transformer, of single-phase transformer, and we're going to apply it here on a three-phase transformer. So, E line to line in the secondary side is equal to E line to line in the primary side, but through the turns ratio, because it's a transformer first. This is secondary, so it will be NS over NB, right? Times E line to line primary. Now, until now, so far, this equation is true for delta-delta connection and also true for Y-Y connection. In case of Y delta, no, we have to add something because now you're moving from Y to delta. And there is a difference in magnitude between them, which comes from the phase and line. So basically here, we're going to have to divide by root of 3. That's the relation between line-to-line primary voltage and line-to-line secondary voltage RMS values. There is a phase shift here of minus 30 based on the sequence. But let's focus now on the RMS values here. Only the RMS values, the magnitudes. But there is a phase shift, there should be a phase shift here of minus 30 degree. Why? This phase shift, if we go back to lecture of week number 9, three-phase circuit, we will notice that there is a phase shift between phase voltage and line-to-line voltage when it comes to Y connection. And that's the idea here. It's Y and we're moving to delta. So there is a phase shift of minus 30. Focusing only on the RMS values, we can calculate it directly from the equations here. Okay? So that's our golden equation for Y delta connections. Now, once we know the voltage, we can also find the current through the turns ratio. Remember, we are transferring the same power, assuming ideal transformer. So what will be the currents? Then the currents will be I line in the secondary, which is this current. So this is I line in the secondary, I small a. This is I line in the secondary, IA, IB, IC. Again, IA is equal to IB is equal to IC in RMS values. And there is a phase shift between the three currents here, plus minus 120 from three-phase circuits. Now, I line secondary is equal to turns ratio, and it's opposite to the voltage. It's going to be NB over NS times I line primary, and again, now we're not dividing by root over 3, we're gonna multiply by root over 3 here. So let me do it here. We're gonna multiply by root of 3 I line primary. Okay? So that's the relation between secondary line currents, here, this currents, and primary line currents, which is this I capital A, I capital B, I capital C. So this is the equation how we found the voltage, and this is how the equations how we find the currents, right? Are we missing something here? The phase shift, yeah. There should be also a phase shift between I line secondary and I line primary, which is minus 30 for the delta there, right? But if we focus again on the RMS values, we can find it without the minus 30. So this is the third type of connections, Y delta. Okay? Okay, this one example, the primary winding of a delta star, so that's our transformer connection is delta star. Primary is delta, secondary is a star. 50 volt ampere, that's the rated apparent power. Remember, volt ampere is the complex power, it's the magnitude of the apparent or complex power in volt ampere, S, capital S. Transformer is supplied with a 100 volt 60 hertz three-phase source. So the transformer is supplied. The transformer is typically supplied in the primary side. So this means this is the E line to line in the primary side. That's the frequency of the source. American standard three-phase source. The transformer has 500 turns on the primary winding side. So this means the 500 is in the primary, in B. And 100 turns on the secondary winding. So this is going to be in S, number of turns on the secondary side. Questions? Calculate first the transformer turns ratio. Whenever we ask typically about transformer turns ratio, it means find how much is in the primary over in secondary. That's the turns ratio, and typically they call it A, right, in the textbook. But don't worry about this. Now we can just keep it NB over NS, right? So what is NB over NS? Basically, this is 500 over 100. That's 5. This is 5. What about opposite of that? NB over NS. There's another way of saying opposite of that turns ratio is NS over NB is basically opposite 100 over 500 or 1 over 5, which is 0.2. So depending on what you need to use in your equations, whether NB over NS or NS over NB, you can use any one of them, as we will see later. So one is done. 2. The secondary side line voltage. So what we're looking for here, the line to line voltage where? In the secondary side. So let's go back to the previous recording videos, previous parts, and we recall our equations for delta star. So what is our equation for delta star? E line to line secondary is NS over NB, right? E line to line secondary is NS over NB times root of 3 E line to line primary, right? This is our equations. So if we put the numbers, this is NS over NB is 0.2 and root of 3 is there. Line to line primary, what is line to line primary? It's given in the question, 100 volt. 100 volt. If we multiply this is almost 1.73, so this is going to be 173.2, it means 173 over 5. We're talking about 173 over 5, we're talking about 34.5, something like this. 4.7 maybe, 34.6 average volt. Right, so let's do it by calculator and check. It should be around this. 34.6 voltage. What is this? Line to line in the secondary side. Remember, secondary side is what? Star connection. In the star connection, we know that there is a difference between line to line and line to neutral, or line to line and phase. Always line to line in a star connection is greater than the phase by root of 3. Okay? So number 3 is saying find the secondary side phase voltage. There we found line voltage in the secondary side. What about the phase voltage? Easy. We go back to the lectures of 3-phase circuits. We know the relation between them, that E phase is E line to line over root of 3. We know this in the star connection. Remember, we are still here in the secondary side, which is Y connection or a star connection. So in a star connection, it's line to line over root of 3 gives you the phase. So this will be, this means E phase in the secondary side is line to line, which we just calculated, 34.6 over root of 3. So again, we're dividing 34.6 over 1.73. This is 20 volt. So that's the voltage in the secondary side. Note that this voltage should be always and always less than the line voltage. We know line voltage is always greater than phase voltage. In Y connection. In delta, they are the same. Right. Number 4. The secondary side line current. Secondary side is the star connection. And we need the line current there. Now, what is given in the question here that can help us to find the current? We know the voltage. We need to calculate currents, right? But there is no any current given here. So, in order to calculate current, you need to look for power, basically. Any given value for powers. We have this. The rated is 50 volt ampere. That's the apparent power of the transformer. And we're saying that we're assuming the transformer is ideal. So this is the apparent power in the primary, and it will be transferred to the secondary, delivered to the load. So remember again from 3-phase circuit lecture, S of a 3-phase system is root of 3, I line, E line. So from here, what we're looking for here is secondary line current. So what will be currents? I line in the secondary will be S of a 3-phase over what? Over root of 3 E line to line secondary, because we are on the secondary side, right? Yeah. So what is this? 50. This is given in the question, 50 over root of 3 over root of 3. We just write it. This is 50 equal to 50 over root of 3 line to line secondary. We calculated this somewhere. That's line to line secondary, 34.6 volt, and this is 50 over root of 3 over 34.6. This should be less than 1, maybe 0.9, 0.8, 0.8, and there is like 0.33 times. Yeah, so this is almost 0.83. what? Ampere. 83, it's the third there, so it's 833, let's see. Ampere. So that's the secondary line current. That's the star, right? The secondary side is Y connection. What about if I ask you about the secondary side phase current? This is the secondary side line current. What about the secondary side phase current? Let's think about it. What is our connection in secondary side? It's a star, it's Y. What's the relation between the line current and the phase current in star connection, in Y connection? They are the same. They are the same. Go back to our lectures about three-phase circuits. That's why here it's not requested in the question. If I ask you in this, you would have to say basically the secondary side phase current is equal to secondary side line current because it is a star. It is Y connection here. What about the primary side line current? We can either apply the same formula here, but because S is the same in primary and secondary, assuming ideal transformer, it will be root 3 again. We're looking for I line, but I line this time will be for primary. Then you have to multiply, you have to divide here by E line to line primary. And it will give you the value of the current. Alternatively, we can use the turns ratio from our previous parts of explanation. When we go back to our equations, what's the relation between the primary or the line, the primary line current and the secondary line current? Go back, recall the equation from delta star transformer. The line in the primary is equal to NS over NB times root of 3 line in the secondary, right? Remember when you check the equations there, remember we started by I line secondary in the equation. That's why it was over root of 3. Here, I changed it. I just flipped the equations. Easy, come on, right? Yeah. So, what will be this? NS over NB, how much? NS over NB, we just calculated, that's 0.2 times root of 3. And I line secondary, where is I line secondary? I line secondary is this, 0.833. So this is almost 0.29 maybe. 288, let's say 289 ampere. That's the primary side line current. Okay. Number 6, the primary side phase current. Okay, let me check. What is our connection in the primary side? Delta. Right. What is the relation between the line current and the phase current in delta connection? In Y connection, they are the same. In delta, they are not. Line current is always greater than phase current in delta connection by factor of root of 3. So, we're looking here for what? For the phase current. So, we know that I phase in the primary is equal to I line in the primary divided by root of 3. So, this is 0.289 over root of 3. This is going to be 0.1, maybe 66, let's say 67 ampere. And here is the solution. Here's the solution of examples, right? Okay. So, we'll put some assignments on these connections. Hopefully this week or next week. Okay. So now, as a summary, we talk about the 3 conventional type of connecting 3 single-phase transformers to 3-phase connection. Y, primary is Y, secondary is Y. Delta, primary is delta, secondary is delta. Delta Y, primary is delta, secondary is Y. Y delta, primary is Y and secondary is delta. And you need to know the equations for all of these 4 connections, voltages and current. Okay? Right, I'll see you in the next week, the next lecture about induction motors. Thank you, and good luck with your exams.